for a significant number of those sequences, they have very high confidence. And another aspect we really care in biology is how how unique these structures are compared to already existing and predicted structures. Because we said that structure implies function. If we can have a new structure, this would imply a new function. So they see that for a significant proportion of those 225 million sequences, they can have a very low score on the sequence identity. So 100% sequence identity would be it already exists. 0% would be it doesn't exist at any degree from the training data. Because all these sequences are sequences that the model has never seen. So it's kind of unseen data, out of distribution generalization. You can call it different ways. So overall, I would say that all these protein language models are something very new, and many things will come up, and they are really a promising research avenue if you ever want to work in this type of application. And representation learning is the essence of pre-training protein language models. So now we will check the internal representation. So far I showed you like some output visualization. So now we will check the pre-trained language models, the internal representation, which are the attention maps. So again, instead of having words here and modeling interactions between words, we take this output of the model before the multiplication with the values, and we have as many attention maps as the number of layers multiplied from the number of heads per layer. So each attention map already gives us a probability distribution of how this specific token attends to all the other tokens in the sequence. The question is, how useful are these attention maps? Okay, I've already showed you the contact prediction. This was like a small glimpse, but now we'll study this a bit more extensively. So here you can see the property of binding site. So this part is the so-called binding site on the 3D structure of the protein. And this is how, let's say globally, these orange lines indicate the attention between all the other amino acids. And you can see that the model already attends, all the surrounding tokens attend in this very important part of the protein, which is the binding site. And this happens only based on the sequence information. And this is a small addition. This is just for one of all the heads, average between the test data. So this 7 corresponds to layer, and this one corresponds to head. So if you have this matrix from heads and layers, I think the first one corresponds to layers and the second one corresponds to heads. But this is just a visualization. We will see more metric. And here you can see these orange lines now indicate the contact map, so what binds to what. And you can already see these global interactions. So even though some sequences are close on the primary structure, so in the sequence, they are neighbors in the sequence. On the 3D space, the image looks completely different. So this is what they did. They took like a random disjoint test set from the PDB, which are experimentally validated 3D structures and sequences of very high quality. and they took different BERT protein language models. And they find out, similar to natural language, that there are some special, at least in their scale of analysis, they found that there are indeed some attention heads that really specialize to specific amino acids. So here we have again the illustration of layers. Let's take this one. So we have different layers and different heads, and you can see at some cases, in some cases, you have these highly blue heat maps, which refer to very high probability. And to illustrate how much, what does 45% means, here they provide the frequencies that statistically the amino acids attend to each other are always below 9.4. So predicting with assigning with such a high confidence, such a high percentage, means that these heads are kind of specialized. Is that clear why this confidence is so important? Nonetheless, this analysis, they have a lot of plots. I will try to be a bit quick. This analysis was performed on individual heads from individual layers and already identified this idea of specialized heads. But still, this is related to different amino acids. And this is again the same analysis, but now we care about the contact maps. So we have a different property, and we see that indeed there may be some heads that on average, based on the test data, specialize on some task. So on the contact maps here. These are just even more illustrations to see this is true for across different models. And regarding binding sites, you can see that many heads from different layers attend with a very high probability into this area of interest, so this point of interest, which is the binding site. So you can think of this binding site as if you have like object detection and you have like a huge image of 1000 by 1000 while the object is kind of localized, how different parties would attend to this area of interest. Or these attention maps we saw that the model learns in vision that kind of encode the foreground and the background on the last lecture. So in general, attention heads do learn something. They do have useful information that is captured, and depending on the task, for example, the binding sites, they can, many heads and from different layers can use assign a lot of attention probability, or in the case of contact maps, some very specialized heads do the heavy lifting. And here they just took different proteins, so because there are 20 different a specific number of proteins, you can assign one different letter to each protein, maybe this is amino acid, and create like a general heat map for all the data sets. So you take this heat map of this protein or amino acid. Yeah, this is amino acid. And this is like 20 by 20, so the 20 amino acids. Sorry for the mistake. And then you can kind of correlate two heat maps from different proteins and get another heat map which would be the pairwise relationship between all the amino acids with a given transformer for all your test set. And they compare this one to the so-called substitution matrix, which this is one where you get from bioinformatic analysis based on statistics and analytical methods. And this is the one based on the transformer. And they saw that you get a similar, let's say, qualitative perspective or image. So indeed, only from sequence data we can capture structural properties, we can even see how these weights target binding sites. They are consistent with the standard analysis from bioinformatics, as we saw with the substitution matrix. And the fact that like for higher level tasks, like contact map prediction, the highest layers capture, the specialized heads are usually the last layers for high level tasks because they have more abstract representation. So now, we have 30 minutes, okay. So now we will see how we can combine attention maps for different tasks like contact prediction, histogram prediction, instead of analyzing what each individual head is doing. So this is another analysis which is closer to the one you will do in the exercise class, where they consider different models. They can consider the ESM version 2 because it was not published, it's from 2020. So this is the ground truth from contact prediction. So this is the L by L binary map we discussed. So one is these I and J bind together, and it's basically symmetric. So if you know the other triangular side, you just copy the elements and you have the whole L by L matrix. And this is the predicted contacts they found. So the question is how to do that, because the amount of information that you get is much, much more. So you have M layers, 8 heads. Your input is X, and you have a length L. We will use the letter A. So the attention map from layer M, non-capital, and 8. This one. So how many, just to make sure that you're all following, how many, for a given transformer model, how many attention maps we get for one input sequence? Yes?
I guess n by h.
Yes.
Times h.
And this is n by n. So let's solve the problems one by one. Problem number 1. The model has no constraint to produce the ground truth. We said it's symmetric, so position ij is exactly the same as position ji, but the model has no information whatsoever or any constraint to produce a symmetric map. So what do we do? In linear algebra, if you have a matrix, let's focus on one individual matrix, an L by L. How can you make it symmetric? Any idea? Does anybody remember? Yes?
You can calculate take the product with the self transpose.
Yes, this is also possible. Yeah, so what you suggest is this one, right? This is also true, but it's what we do is slightly different. But in general, in the first step, you need to symmetrize your attention map. So we do A. Suppose I think we divide it by 2. So it's the second way, which is the preferred way to do it, but what you said probably also is possible. Okay, so now all the attention maps are symmetric. Maybe not the best way, maybe we'll find another way, but at least it looks like the way the output looks. So in this paper that's called Transformers are Transformer Protein Language Model are Unsupervised Structure Learners. So you see the attention maps here. This S stands for softmax. Here you see the stop gradient because we just use them as an input, we don't propagate any gradients. So you see symmetrization first and then APC. So APC is, stands for Average Product Correction. And it's defined, it's applied independently, both operations are applied independently for all the n/8 attention maps. And is computed as follows. So let's say APC, Average Product Correction. So I is the row of the index of the row, J is the index of the column, and this is the full matrix. So this is the row sum. So for row I, so if we want to, if we take this element, the Fi would be the sum of this row. This would be Fj. And this would be the sum of all the elements on the L by L matrix. So you can think of this as some sort of normalization step. It's not 100% clear to me what is the intuition behind it, but we did some visualization in the lab and we saw that even visually you see a much clearer picture of the predicted contacts. And if you remove it, you have some sort of row-wise, column-wise or row-wise noise.
One question.
Sorry, yes?
Is the F just a normalized A?
F is the sum of the whole L by L matrix.
Ah.
Yeah, I use the word F, but basically it's A. So the attention maps. So the symmetrized attention map, you subtract all the rows and the row-wise sum, you subtract this value. Yes?
When you say row-wise sum, do you mean Fi times Fj, or the sum of Fi times the sum of Fj?
Yeah, both. This is a product divided by the total sum. So you need to compute these values and these values and the whole. You need to compute all three values for each position. And then we want to discard as many. So now we remove the noise, we made the symmetry, we remove the noise, but now we want to see which of those attention maps are useful. So useful depending on what? Depending on the task. So we have this contact prediction. And we do a regression, like logistic regression. I have some notes. So how do we do that? We have these n/8 attention maps, and we assign a shared weight for the whole. So this weight is position independent, so ij independent. So W1 corresponds to the the first head of the first layer, W2 the second head of the first layer, and so on. So we have these weights that are position independent. So now we don't want to see the individual contributions. We just want to see which of those maps are the most useful. So we do this binary classification. So we train these weights with logistic regression. But then on top, we apply a regularization, which is called L1 regularization. I have some slide about this. No. And the question is why the authors of this work choose to apply L1 regularization and not just logistic regression to find the individual contribution of those weights. What do we gain by additionally constraining the weights with this term? No ideas? Okay, I will help. So L1 regularization. So by the way, these are the map for logistic regression. So these are the weights that are position independent, so there is no ij index. This is W on the slide. It's called beta here, and these are all the different ij for different heads for different layers. So L1 regularization is for different weights, which correspond again to different attention maps. And it's different from L2 regularization, which would be something like this. So I will tell you the answer, then we'll try to come up with why this answer is true. So if you read any interview-based question, they will say, why do we apply L1 regularization? And the answer would be because it leads to sparse weights, which means that many of the weights will become zero. Does anybody based on this can see the different behavior and why that is the case? Why we will end up with a lot of zero weights? So if we take the gradient, it would be something like this. So this would mean W1 divided by the length, the magnitude or length, and then W2 divided. So in this example, and if we try to derive some intuition, is that basically the sign, so the gradient here, is not dependent to how big or large these weights are. So all the weights will be scaled down. They will have smaller values because we regularize them, independent of how big or small they are, which is in contrast to L2 regularization, where if you take the gradient here, is dependent on the weight. So here all the weights will be scaled down, but based, here it will be based on a constant factor of 1, but here we will scale the weights based on their values. So we penalize much more the the big weights when we do L2 regularization, which is what we do in standard neural network supervised, self-supervised pre-training. But here we do L1 because we want to push to have like a sparse solution to discard as many attention maps as possible. And the visualization here looks something like this. One, and one. So this is the loss, the regularization term, and the gradient would be either 1 or -1. So here from the gradient you can see that all the weights will be scaled up and down basically, independent of their value. Is that clear why L2, L1 regularization leads to sparse weights? Any questions? No? Okay. Okay. And then we just select the one we want, and then we just take the average, like in the next step. So in this step of logistic regression, we decide which weights are the most important, and then we just take the average. Then we try to do some analysis based on different layers and different heads, and they found out different behaviors depending on what type of distances they want to predict. We'll not cover so much about it. However, there is some ex-collaborator of mine who did some similar work on proteins and antibodies with protein language models, and he found some really interesting results. So based on his test set, he considered all the contacts that are really unlikely to happen with a probability between 0 and 0.001. Here some contacts that are much more likely, but still like medium likely to happen, let's say. And here are the contacts that are really frequent. And he saw that the model performs extremely poorly here, mediumly well here, and on top, for those who are interested, he found out that the protein language models, even though they have never been trained on this sifted data distribution, which is antibodies, by only being trained on sequences, they were able to perform extremely better, or significantly better. And here, all the models perform, they are able to capture all these very frequent statistics for different contacts, independent of the different models. So the gist here is that the bottom line is that rare contacts are extremely hard to predict, even with the largest scale models. And here are again this analysis between layers and heads. So here white means that the weights are discarded from regression, and the non-discarded are visualized from these ranges of colors from blue to red. So you can see already that there are just a few weights regarding contact predictions that are very useful. Okay, I see that the same image on my computer, I can identify much more heads. But okay. Yeah, I also have the number. So only 102 out of 660 are the ones that are the one that they found by logistic regression, that are ones that are contributing to contact prediction, and all the others can be discarded. And again, that based on the previous analysis of different heads on different subtasks, that they are attention maps that specialize at different ranges of prediction, which I just want to re-emphasize this idea of attention heads learning very specific functions. And the last part, which is a bit more to give you like a very broader scope of happening, like some really recent work from the Baker lab, is that they took these protein language models and they tried to use them as a generative, in a generative way to produce artificial proteins that could lead to new drugs and new vaccines and stuff. And surprisingly, is there any question? So surprisingly, they took these 660 attention maps from these layers of this ESM2 model that we saw before, and they applied a linear layer based on all the 660 features from all these attention maps, but a shared linear projection. So for position ij, they took this vector of m by 8. I don't remember how many heads and layers, but their product is 660, and they applied a shared linear layer with which is trivial to train, like I think less than 15,000 parameters, and the target was the histograms. So not the contact maps, which was the binary thing in this L by L matrix, but they instead considered a histogram between 18 beans, so 18 classes in the classification task, where the first bean corresponds to all the proteins, all the pairs, position ij, that correspond to distance from 2 to 3 angstroms, and then class 2 is 3 to 4 angstroms, and so on. Is that clear? And they saw that they were able to predict the histograms quite well for their considered data set. And even a linear layer without coming up with a very sophisticated network. If you have this largely pre-trained ESM2 model on billions of amino acids, you can already get some very good protein structure. Yeah, this is the information about the binning. So they have this 16 beans, and this is the rangings from 2.5 to 20 angstroms with 1 angstrom difference. And then they use it for different generative tasks, which was unclear how generative can a protein language model be. So they considered 2 different setups. So the first one was to say that, okay, we want to create a protein that looks like this on the 3D space. Find us the sequence, so the primary structure. And the other was, okay, you can both change both the primary structure and the tertiary structure. And they tried different setups. I will provide some information. So here you have this same contact prediction visualization, where this one is the ground truth part, and this one is the one predicted from the model. This one is also another thing we haven't discussed about. So by masking during inference, if you mask one of the, so here, so let's say the model is already trained, and you mask this token, and you predict a probability of what is the best possible candidate from these 20 amino acids to be in this position, and this already gives you like a probability distribution, and it's a way to find possible new candidates to design new proteins. So let's say if amino acid number 1 was here, and the protein language model predicts here an amino acid, let's say number 4, maybe this kind of mutation, if we experimentally design this with a specific mutation as indicated from the top candidates of the language model, we can design novel protein with novel structures and functions. And for the tertiary structure, they just use the linear layer to predict these results, to have all these pair-wise distances. So the nice thing about this work is that there is like a huge bio-machine learning team, and they not only predicted some candidates and structures, but they also experimentally validated those possible candidates predicted by the protein language model. And all the green ones are some TSNE visualization. But all in all, I would like to emphasize on the fact that they produce novel sequences, novel 3D structures, so novel functions, as identified by a sequence identity. So the lower the sequence identity, the more novel the structure and thus the function. And you can see they had some success with very, very low sequence identity of 22%. So the core findings from this work is that they were able to design the so-called de novo structures or novel structures, and they also re-emphasize on the fact that this protein language model kind of materialize and encapsulate these underlying principles that led from many, many years of natural evolution, and this model were able to capture, and not just to capture these relations as themselves, but also generate novel structures that might lead to new drugs, new proteins with new functions. Okay, so what are the limitations? I've just shown you how amazing these models are, but as everything, they have some limitation. So the first limit comes from the most dominant module, from attention. So attention has this quadratic complexity, and we are still not able to scale these to very large sequences. So even in biological data, you may have proteins of 3,000 or 4,000 sequence length. I'm speculating, I don't know the exact numbers. So this would be very hard. These are still like a computational bottleneck that comes on par with the attention mechanism. And the thing is that if the model is trained on a maximum sequence length, let's say of 1,000, it's not clear how this model would perform on larger sequences, even though the transformer by itself can process any type of sequence length. We saw that these positional encodings or positional embeddings that are learned for each position are fixed. So you are a bit constrained on the maximum number of sequence. When the model is trained with a maximum sequence of 1,000 and it has like positional embeddings, you cannot use this model. There are ways, but you cannot like inherently use the model as it is. The other thing is that storing 660 attention maps of L by L for each individual sequence, if you had 50,000 sequences like a test set, would result in terabytes of information. If you do the math and all these values are floating points, you can see that you already get in a tiny subset, test set, you can already get terabytes of information, which is infeasible to store locally on hard drives, even on the cloud. It would be highly costly. So these largely pre-trained transformers are kind of a compressed version of all the sequence they have seen. So it's impossible to store these maps. Then it's about symmetry. So right now we do this symmetrization trick, like the cheapest possible trick we could do, but the model doesn't really encapsulate all the physics or respect the rules. So for example, on DNAs and RNAs, you have some rules. For example, the base, for example, adenine, it's called A, binds to, I don't remember exactly, but only U and not, for example, Z. And this is not, this rule-based physics-informed information is not guaranteed from the model. So there might be future methods that take that into account. And as a result, physical rules that proteins, when proteins are transcribed and translated from DNA to RNA to proteins, they have this, this jittering folding procedure. But we only predict, let's say, the last frame, so the last 3D structure, the result of this jittery folding process. I don't know if you've seen the videos that I send you. Usually there's a lot of jittering for these proteins to bind and translate and transcribe. And we know that all these language models have very, very limited understanding of this folding procedure and the trajectories that proteins follow. So I just want to keep that in perspective. And last but not least, the rare contacts. So even on billion scale amino acids, there are contacts and stuff you will not really see very often, which are extremely hard to predict. That's the end. Any questions?